Uh, Hello, teacher and everyone. We are group 15 for the ITI course. Today, we are going to present our project on the topic which sentiment process extraction. Uh, our team consists of three members: me, Hứa Vĩnh, Trịnh Minh Anh, and Nguyễn Thành Tâm. Our presentation will be next slide. Uh, our presentation will be divided into 8 sessions. First is problem definition. The second is input output identification. The third data present preparation. Uh, then optimization technique, model architecture, and training performance evaluation. And then we will discuss about interfere on new data, and finally is conclusion. Moving to the first part, problem definition. Since its launch in two, 2000 and 2006, Twitter now rebranded as it has emerged as one of the most influential micro blockchain platforms. It is a space where hundreds of millions of the users express their opinion on every from social issue and politics to support and trending topics. This massive volume on monthly active users generates a vast stream of short-form text data. This data is rich in emotional insight, making it highly valuable for public opinion analysis, brand monitoring, and studying user behavior. In this context, sentiment analysis is widely utilized to identify user attitudes. However, traditional methods typically stop assigning a global label to the text, such as positive or negative. This approach often falls short in practical application, particularly in customer experience analysis. Because it lacks explainability, it doesn't tell us why a user feels a certain way or which specified words trigger that emotion. Therefore, the challenge we are addressing is not just determining the settlement of a twist, but identifying the specific process within the text that defines sentiment. This is the first of the twist sentiment process extraction problem. Uh, for the next part, input output identification. Next, let's look at the input and output identification. To solve this machine learning task, we define our data as follows. Input, we have two components. We have two main components: the twist content, which acts as our context, and the sentiment label, which acts as our question. Essentially, the model receiving the full text of the twist and the predefined sentiment, positive, negative, or neutral. For the output, the model is expected to provide the start and positions within the original string. This position correspond to the specific price or the span as serves as the explanation for sentiment label. In our dataset, this is referred to as the set text. Uh, for the next part will be presented by Trịnh Minh Anh. Please, Anh.
Okay, moving to the next step is data preparations. The first one is inspecting data. In the first step, we explore the datasets using the pandas head. function to obtain overall understanding of their structure and key characteristics. The training set contains 27 and 480 samples with 4 columns, including text ID, text, selected text, and sentiment. Among these, selected text is manually annotated phrase that directly expresses the sentiment of the tweet. This span is target output that our model aims to predict. The testset consists of 3,534 samples and includes only text ID, text, and sentiment. Importantly, it does not contain selected text as this set reserved exclusive for model inference. The tweet content is highly diverse, ranging from very short messages to tweets containing URLs and special characters. From the data exploration, several important observations can be made. Next slide. First, this task is not a standard sentiment classification problem, but rather than span extraction task, where the goal is to identify the exact text fragment that supports the sentiment. Therefore, token-level or span-based models are more appropriate than models that only predict sentiment labels. Second, the tweet data is highly noisy, containing URLs, punctuation, and informal language. For this reason, we adopt subword tokenizers such as BERT or ROBERT, which have reduced unknown tokens and handle rare or non-standard words more effectively. Moving to visualize data. This illustrates the distribution of sentiment labels and tweet lengths in the training set. Next slide. From these visualizations, we identify 3 factors that directly influence on training strategy. The first one is label distribution. The data is imbalances, with the neural class occupying the largest proportions, about 14%, followed by positives 21% and negative 29%. Next one is text length. Small tweets contain fewer than 64 words. However, due to robust bi-level BPE tokenizer, the number of tokens is often higher than the word count. As a result, we select mark length equal to 96 or 128 to capture all relevant information while avoiding unnecessary computational overhead. Last one is moving on to the data preparations. The biggest technical challenge in the pre-processing step is alignment issues. The ground truth standard label is assigned at the character level, but the transformer operates at the token level. A single word may be split into multiple subtokens. The risk is if alignment isn't handled correctly, the model will learn the wrong start and end positions. So the solution for this is offset mapping. During tokenization, set the start char, end char pair for each token, and we will use this mapping to convert character level span to token. In this ensures accurate supervisions during the training processes. So moving on, the next step is optimization techniques. The first one we want to mention is the neural trick heuristic rule. Based on the insight we mentioned above, the neural tricks is applied if the input is labeled neural. The system bypasses the model span prediction and directly returns the entire text. This heuristic boosts the neural Zaka score to near perfect, about 0.97, allowing the model to focus its learning capacity on more challenging positive and negative cases. In addition, the A post-processing step is applied to ensure output validity. If the model predicts an end index smaller than the start index, the algorithm automatically selects the text valid index pair with the highest combined probability. So that is the end of my part. The next part will be presented by Tâm.
So continue with the main part. I will present to you about the model architecture and training. This is our model architecture and training. The first one we have the pre-processing data. Next one we will have the robot-based block, and after have the final output, we will use the k-iteration, k-fold, and after that we will use evaluation parameters to evaluate output of our model. So with the model architecture and training, with the key concept, we have the pre-training as a robot A because it has read 160 gigabyte of textbook internet before we even started, giving it general knowledge. And the reason why it worked for Twist, first one is the data. It trained on 10x more than BERT. So second part is tokenization by level BPE. It's crucial because it's a standard for model fail on image or weird character. Robot breaks word down into bytes and character. It can read any complex text file on Twitter without errors. So let me explain to you about how it works. First one, we will have the training dataset as we have been provided. With the input data, we normalization it and format it. After that, we will use the bi-level BPE token to split into subword as the Ming mentioned previous slide. After that, we will use the BERT tokenization neither with the offset mapping as the key factor with an token IDs and attention marks. Next one, after pre-processing, we will come to the robot-based block with the robot-based block. Reason why is the backbone is a robot-based encoder. As we have here, in robot-based encoder, we will have the contextual embeddings. After tokenized step, each piece is converted into a sequence token IDs. So when it passes through robot A, each token is no longer discrete number, but it becomes contextual embedding vector. And this vector depends on surrounding context, not static meaning. For example, I am so happy today. After bi-level BPE, it's come to the array with 7 elements. Then the robot encoder will have the x1 to xn embedding vector. And with the architecture, after that we will after robot-based backbone, we will combine it with a linear layer with a QA head because linear layer acts as pointer predicting two numbers probability of being start word and probability of being the end word. How the start logic and end logic work. For example, the so set I will miss you, the token at 0 start at logic at I present here at the 0.1 and end logic is 0.2. We will continue to token n. The result is token index 1 set has the highest start logic and highest end logic. After we have the final output, we will have the training strategy as Ming mentioned at the part 4, which is stratified split. Data is split, ensuring balanced sentiments. Representative functioning, because the computation limits we employed a fivefold validation as I described in the image here. After that we perform at the formula that I pointing here. It's aimed to increase the stability and reduce variance, and we use fivefold cross-validation. The next part is the experimental and result. To evaluate the experimental and result, we will come back to the evaluation parameter. At three elements here, we have the word level, Jaccard score, exact match, and length difference ratio. So with the first one, we will have the visualize analysis with the Jaccard distribution of massive peak at 1.0. With the mode twist, especially neutral model retrieve the phrase perfectly, and sentiment breakdown with the extremely high performance at the median approximately 1 due to the optimization trick. The positive and negative also capture effectively in subjective phrases, though with slightly more variant as these are harder to define. With the length of cooperation, we have the predicted length close follow the true length, proving the model understand boundaries well. And moreover, the final score, our optimized model achieved a Jaccard score but nearly 0.7, surpassed the baseline 0.68. With the inference on new data part, we have the new data for inference. 5 manual inputs and 45 random test sample at the test.cfv provided. With the neutral label output, select the entire sentence. It is correct, no emotion bearing keyword. Model has learned this rule accurately. Negative label output extracts the key negative token, precise, not the full sentence. Positive label output correctly identifies the positive and positive adjective. Summary that we have Robert learned text semantics very well. The strong performance display in training and reward inference. Our strength also perform that accurate, classify sentiment and pinpoints key phrases. The correctly applies dataset rule for neutral selects the full sentence, as we have the image display here. The fun part is the conclusion. With the overall performance, the proposed model achieved the 0.68, significant outperforming the prioritized study. As the two paper I put it in here, our model with the and moreover in the NLP competition, start improvement that again represent a major performance leap. And moreover, I have the learning capability with the strong improvements on positive and negative sample. It concludes that effective sentiment phrase extraction with the full sentence prediction and exact match is more than double. It proved that our model certain substantially higher precision. With the stability, neutral performance remained high and slightly improved, showing no catastrophic forgetting on simple cases. To conclude that we have the built end-to-end system transforming robot A from a classifier, ennator, and extractor. With the key takeaway, we have the correctly framing the problem as question answering and applying domain-specific rules is more than effective than just make the model larger. With the future work, we will explore model distillation, making the model smaller and faster, with the fivefold example where resources permit. Finally, that is the end of my our presentation. Thank you for listening.